Hey, seventh graders, lesson 2 for our new unit on or new chapter, excuse me. Sometimes I get math and science confused. New chapter on plate tectonics. So, this one's called Seafloor Spreading. We're going to read about Marie Tharp, who is our My Planet Diary discovery today. Have you ever tried to draw something you can't see? By 1952, geologist Marie Tharp and Bruce Heezen had set to work mapping the ocean floor. Tharp drew details of the ocean floor based on data taken from ships. The data showed how the height of the ocean floor varied. Tharp's maps, which were first published in 1957, helped to confirm the hypothesis of continental drift. So obviously they weren't drawing from the bottom of the ocean because they cannot hold their breath that long. But so her maps showed how the height of the floor varied because she learned that data from ships. Okay, 3 key questions today. What are mid-ocean ridges? What is seafloor spreading? And what happens at deep ocean trenches? So, a mid-ocean ridge is an undersea mountain chain where new ocean floor is produced, a divergent plate boundary under the ocean. So, 2 different things there. The mid-ocean ridges form long chains of mountains that rise up from the ocean floor. In the mid-1900s, scientists mapped mid-ocean ridges using sonar, a device that uses sound waves to measure the distance to an object. So they would know if they hit one because the sonar would hit that. Seafloor spreading is the process by which molten material adds new oceanic crust to the ocean floor. By the 1960s, scientists had learned more about mid-ocean ridges. Seafloor spreading begins at a mid-ocean ridge, which forms along a crack in the oceanic crust. And seafloor spreading adds more crust to the ocean floor. At the same time, older strips of rock move outward from either side of the ridge. So, some evidence. So, evidence from ocean floor material. In the central valley of mid-ocean ridges, scientists have found rocks shaped like pillows. Such rocks form only when molten material hardens quickly after erupting underwater. So like an underwater volcano. From magnetic strips. Rock on the ocean floor forms from molten material. As the material erupts, cools, and hardens, magnetic minerals inside the rock line up in the direction of Earth's magnetic poles. These minerals form unseen magnetic stripes on the ocean floor, but the magnetic poles occasionally reverse themselves. So each stripe defines a period when molten material erupted and hardened, while Earth's magnetic poles did not change. Scientists found that the pattern of magnetic stripes on one side of a mid-ocean ridge is usually a mirror image of the pattern on the other side. The matching patterns show that the crust on the 2 sides of the ridge spread from the ridge at the same time and at the same rate. So it doesn't go like, it goes whoop. All right, so I do not know why. There we go. Okay. Evidence from drilling samples. Scientists drilled into the ocean floor to obtain rock samples. They found that the farther away from a ridge a rock sample was taken, the older the rock was. The youngest rocks were always found at the center of the ridges. Recall that at the ridge center, molten material erupts and cools to form new crust. So the rock's age showed that seafloor spreading had taken place. Next vocab word is deep ocean trenches, a deep valley along the ocean floor beneath which oceanic crust slowly sinks toward the mantle. In a process taken tens of millions of years, which not quite that much, part of the ocean floor sinks back into the mantle at deep ocean trenches. As it moves away from the mid-ocean ridge, it cools. As oceanic crust cools, it becomes more dense. So eventually, as oceanic crust moves, the cool, dense crust might collide with the edge of a continent. Gravity then pulls the older, denser oceanic crust down beneath the trench and back into the mantle. So, some more words. This is a pretty big lesson. So, subduction is the process by which oceanic crust sinks beneath a deep ocean trench and back into the mantle at a convergent plate boundary. As subduction occurs, crust closer to a mid-ocean ridge moves away from the ridge and toward a deep ocean trench. Seafloor spreading and subduction often work together. They move the ocean floor as if it were on a giant conveyor belt. These processes can change the size and shape of the oceans. The sizes of Earth's oceans are determined by how fast new crust is being created at mid-ocean ridges, and how fast old crust is being swallowed up at deep ocean trenches. An ocean surrounded by many trenches may shrink. An ocean with few trenches will probably grow larger. So the Atlantic Ocean is actually expanded. It only has a few short trenches. Just an example. So our vocab words. Mid-ocean ridges, an undersea mountain chain where new ocean floor is produced, and a divergent plate boundary under the ocean. We look at divergent plate boundaries next lesson, so that'll make more sense then. Seafloor spreading is the process by which molten material adds new oceanic crust to the ocean floor. Deep ocean trenches, a deep valley along the ocean floor, beneath which oceanic crust slowly sinks towards the mantle. And subduction, the process by which oceanic crust sinks beneath a deep ocean trench and back into the mantle at a convergent plate boundary. So your assignment is to complete the Edmodal questions for lesson 2. There will definitely be vocabulary words on it. There might be a question about the Atlantic Ocean expanding, and a couple other various questions from the lesson. So if you need to review something or take notes that you didn't take, go right ahead. Let me know if you have any questions. Have a great day.